Okay, so here we are in section 1.4, where we're going to be talking about something called the curse of dimensionality. So what is that about? So in the settings so far in the chapter, we've been talking about mapping a single predictor variable into a single target. So remember that we had some polynomial function that we were trying to fit to some points generated from a sinusoid. And that sinusoid just took one predictor and produced an output, and we corrupted it with noise, and then we tried to fit that. But in real life, you will often be in a situation where you don't have one predictor, you have hundreds, sometimes thousands of predictors. So imagine trying to predict, let's say, someone's a disease state or a health state from gene expression data. So these days we can get gene expression data for hundreds of genes, and you want to be able to map that 100-dimensional, 1,000-dimensional vector indicating gene activation for for a particular patient to their health state. So what happens in those settings when the inputs are high dimensional and sometimes the outputs can be high dimensional? So what happens then? And it turns out that having high dimensions can complicate the situation for some kind of unexpected reasons, for some reasons that can be, well, I mean, counterintuitive is not the right idea, but rather that our intuitions about low dimensions don't extend to high dimensions, and we'll see some examples of that here, and that can affect the algorithms that we write. And finally, we're kind of faced with the fact that despite these problems of high dimensionality, somehow learning is possible. So why is that? And that's kind of what we talk about at the end of the section. So let's just kind of get into it and see what Bishop is mentioned in this chapter. So indeed, as I just mentioned, we've been just working with one input variable, but what happens when you have many input variables? And that's kind of what we're going to be talking about here. So the data set, he's got a nice real life data set. I guess it has to do with kind of an oil and gas data set. He's got 12 predictors. In this particular setting, we're just looking at 2 of them. And you can see that there, you have a bunch of data points. I don't know, looks like hundreds of data points here. And their values for 2 of the predictors are shown, so x6 and x7. And a bunch of them have been labeled. So they've been labeled into these 3 groups, the red, the green, and the blue. And now our task, as always, is to predict for new data what the labeling of the new point, so this x, is going to be. And kind of intuitively, it seems like, well, it looks like it could be red, maybe green, and certainly not blue. So how are we going to make an algorithm that does that? So one natural way to do this would be to split up the space into little boxes, into little regions, and then assign a value to a new point based on the majority vote on the training data for the box it's in. So every point is going to fall inside one of these boxes, and we're going to say, well, a point that falls into this box is green because there are 2 green points and 1 red point, so the majority is green. All these points up here are going to be, any point up there is going to be blue because most of the points in any of those boxes, the overwhelming majority, are blue. And that kind of seems to jive with what what the data looks like. So maybe it misses some of these these blue points down here, but I mean none of this, none of our algorithms are ever going to be 100% successful. And that, I'd say for kind of a first pass approach, it does pretty well. So that's fine when you have 2 dimensions, but the problem arises, and the problem with this kind of boxing approach arises when you have tens of dimensions, hundreds of dimensions. And the basic problem is that for this algorithm to make any sense, we kind of implicitly required there be some decent number, at least, let's say, I don't know, at least 1 point in each box. Right? Otherwise, how are you going to assign a value to that box to then give any new point that lands in it? So you want at least 1 point, let's say, in the minimum, for this algorithm to even make sense and to be applicable. But the problem is that as the dimensionality gets higher and higher, the number of boxes that you create with this approach blows up exponentially. So let's just kind of look at what that means. So in 1 dimension, so we were already talking about 2 dimensions, but in 1 dimension, if you split up your range into three regions, you have three distinct boxes, 3 bins. So if you have 1,000 points, they're distributed evenly. Well, good chances are a good chunk of them, a good number of them will fall into each box. You can run your algorithm as you want. What if you have 2 dimensions? Okay, well, still it's pretty fine, which is kind of, we looked at that example. So now you have 9 boxes. Still fine, we can fill, we can fill it up. When you get up to 3 dimensions, now you're going to have 27 boxes. It's still okay, but you can see that as the number of dimensions increases, we require n to the d, we get n to the d different boxes. And so this is exponential growth in the dimensionality. So you see, if we can just write this as e to the d times something. And that's really problematic because you can imagine that, so let's say ln of n is, let's say, even if that's about 1, if you have d being 100, which is not, which is completely standard, there's lots of data sets that have 100 features, you're going to need an enormous number of boxes. And why is that a problem? Because you'll never have that much data. So how are you going to, many of those boxes are going to be empty, and so and it doesn't mean that data won't fall in them. It just means that your current data set will almost never have enough points to occupy, even with 1 data point, every single of the boxes. So in 3 dimensions, you have 27 boxes. Chances are your data will fall into those. You'll have some data points in every box. But in 100 dimensions, I don't know what e to the 100 is, but it's some enormous number. You're not going to have that many data points. And so algorithms like this, but many others, are not going to work in those high dimensions. So that's one of the real one of the kind of key versions of this curse of dimensionality, that basically the number of boxes, the number of bins that you need kind of grows exponentially, the space blows up, and you just don't have enough data points, if your data points are sampled uniformly, which is the big assumption, to fill all those boxes. So how are you going to make decisions about points that are falling, new data points, which will often not fall into the existing boxes? Okay, so that's one aspect of it. So this exponential growth. Another aspect, very related, is going back to our example where we had targets and we had weights, and we were trying to use them to predict we had predictors. The predictors were x, and we had weights, and we were trying to predict the target y. And again, the target is still here is just scalar. So here is just, instead of being a function of a single variable, imagine now it's kind of a, if it was 2 dimensions, it would be a surface. If it was 3 dimensions, it would be kind of a hypersurface, etc. But this occurs all the time when you're trying to predict. I mean, imagine in some sense it already occurs. No, actually, in a very direct sense, it occurs, in neural networks, right? Let's say the output y is going to be some number, I don't know, determining how the probability that a cat is in the video or something like this. Well, these these x's are going to be, let's say, the pixel values of the images that you're trying to classify, and you're trying to learn some set of weights that will allow you to go from those pixel values to probability of cat or whatever it is. So this is a very, the problem setting here, y being a function of vector valued predictors with some vector valued weights, is a very very, very common setting. And so now what's the problem here? The problem here is that now the number of weights that you need is going to grow up in a kind of a power law fashion. So not quite exponential, and we'll see why that is. You probably can already see it on the page, but still it blows up kind of very problematically. And so let's just look at what this expression is. So we've got a constant term. So far so good, no problem. We have and then we have a linear term, linear in x, and now we have a quadratic term. Now this is the first one that will differ from what we had before. So you remember before that we had in the curve fitting set situation, we only had a single variable x. So that would be equivalent to doing the sum, but only for a single value of I. So and j would so I equals 1 and j equals 1, and that would be it. But we have d values of x, so we have d different variables. So now we have to consider all of their pairwise relations. So not just the one of x1 with itself, which was basically our original setting that we had before, which just contributes an x squared. But now there is d squared, order of d squared possible combinations that we have to have weights for. So now we're getting d weights for the linear terms, d squared for the pairwise interactions, d cubed for the kind of triplicate interactions, and it won't exactly be like d cubed because there are symmetries here, right? Like xi times xj is the same as xj times xi. So for example, there's various combinations of w that will be redundant, but nevertheless, the number will grow with d to the power of 3 in this case. It'll be d to the power of 3, but you might be able to like shave off a factor of 2 or something because of these redundancies. And if you have more and more variables, well, now you're going to have like a d to the power of 4, d to the power of 5. And the way that the number of weights will grow is basically d to the power of m, where m is the largest size of your model. And again, that's going to be an enormous number. So if you have, an order 5 model and, d is 10, so you have a 10-dimensional vector, that's going to be 10 to the 5, so 100,000. So again, there are data sets that are that big, but okay, like let's make M6 or 7, like why not? And all of a sudden you're essentially getting into a setting where you just will not have enough data to fit your model. So it's just that, you get another aspect of the curse of dimensionality, which is kind of this combinatorial explosion that's happening, which is what we're seeing here. There's too many combinations now that we have to take into account, and we don't have enough data to essentially constrain them. So we don't have enough data to learn all those values of wijk. So that's kind of another face of it. I mentioned the issue of our kind of geometric intuition being wrong in high dimensions, and Bishop provides an example of this, and I think he provides it in a very kind of elegant way. So the question that we can ask, and there's essentially the main observation is that, like, if you think about lower dimensions, like 2 dimensions or 3 dimensions that we're used to, most of the mass seems to be kind of evenly distributed within a volume. So there isn't like an enormous only kind of a fraction of the mass of a shape is contained within a shell, near its surface. Now you would think that this would surely be the case as well in higher dimensions, but the really striking observation is that it absolutely is not. So for high dimensional objects, most of their volume is contained within kind of a narrow shell of their surface. So one way that one way to think about this, it has to do with what's called kind of you can think of it as kind of the law of large numbers, or something called a fancier word for it, which is like the concentration of measure. So you can imagine, let's think about the length of a random vector in high dimensions. So lots of the properties of these random vectors, if you pick imagine that random vector in high dimensions is your set of features, and let's say we wanted to kind of compute its length. Well, due to the law of large numbers, when you have lots of those elements and where you're taking their squared values, whatever, summing them up, square rooting them, they will tend to concentrate very much, and they will concentrate more than the higher the number of dimensions. And so that's kind of like saying that the lengths of kind of random vectors in high dimensions will all be roughly the same, and they'll have this kind of like this nearly constant value. They'll be kind of living on a shell. So it's not like in 2 dimensions, where if you pick kind of random vectors in 2 dimensions, their length will vary quite a bit. You'll get points that are all over your surface. In higher dimensions, if you pick the elements, again, the random and the independent selection of those features is a key component here. Their length, the length of the resulting vector, will tend to be very close to some value, and it'll be very sharply focused around that. And that means that these vectors, they're actually all kind of living on very close to a particular shell in that high dimensional space. So almost all of the volume is contained within these extremal shells. And so Bishop kind of talks about this and kind of has a very simple demonstration of that. So what we're going to be discussing in this particular, in his example, is we have a sphere of radius 1, and we're just going to be looking at what fraction of the volume is going to be within 1 minus epsilon, with the radius of 1 minus epsilon to the full radius. So we're just looking at what fraction of the total volume is living within a shell of thickness epsilon from the surface. So the very first nice thing he does is, you can kind of look up the formula for the volume, and it's going to be, it's going to have some, funny constant terms in it. Well, it turns out those aren't going to matter. So he just says, look, the main thing is that the volume is going to scale as r to the d. So that seems very natural, and there'll be some normalizing constant that, due to the integration you need to take into account, but we don't really care about it. It'll just be some function of the dimensionality. So the volume of our d-dimensional sphere is some constant times r to the d. That makes sense, right? So like in one dimension, that volume is just, I guess it'll be 2r, but again, so some function of r. In 2 dimensions, it'll be pi r squared, so something times r squared. In 3 dimensions, it's 4/3 pi r cubed. So again, some different constant. But the main point is that it's going up with the dimensionality. Okay, so now we're going to just compute this ratio. So we've got the volume of the sphere of radius 1 minus the volume, same dimension, of the sphere of radius 1 minus epsilon. And so you can, so all these, so each, all the kd, and then, sorry, and we're going to then divide it by the volume of the unit sphere. Now, the important thing is when we're doing this, this term has the same kd, this term has a kd, and this term has a kd, so they all cancel out. So that's why we don't really care about this normalizing constant. It can just be whatever it is. And then all that's left is just the contributions of r to the d. Well, 1 to the d is just 1. 1 to the d at the denominator is 1, so we can just ignore that. And so the only kind of interesting term is the 1 minus e to the d, which is the volume of the unit sphere of radius 1 minus epsilon. And so what we get is that the fraction, so this is the fraction, maybe I should draw it. So this is kind of our little sphere of radius 1. And now we are looking at, this is, sorry about my drawing, this is epsilon. So this is 1 minus epsilon. And now we're looking at, maybe I should use different colors. So let's say I'm going to use blue for this guy. So this is going to be blue. So that's going to be the whole thing. And now I'm going to use red for this little bit. So that's going to be the bit in here. So we're looking at, kind of what's in this blue region minus what's in this region. So it's going to be all this green stuff. Anyway, I don't know if that drawing helped, but turns out, okay, so all we get is 1 minus epsilon to the d. And now the main point is that pick your epsilon, whatever you want, however the size of the shell that you want. You as d. So this is the interesting thing. You can make your epsilon tiny, right? So you can make a tiny little shell, a tiny thickness, a very, very small thickness. So you're like, surely the volume isn't going to be contained, not much volume is going to be contained in that tiny shell. But it turns out, and again, basically because of these kind of concentration of measure, these laws of large numbers, that, let's see what happens. What fraction of the volume is there? Well, it turns out this 1 minus epsilon, when you raise it to the power of d, so it might start out being very large. It might start out being like essentially 1, like 0.9999, essentially 1. But as d increases, if you take d large enough, this term essentially goes to 0. And so you end up with this kind of very striking fact, which completely opposite our intuitions from low dimensions, that most of the volume of these high dimensional randomly uniformly distributed high dimensional objects is actually on a shell. So it's not within the bulk, it's sitting on a shell. So this is just kind of one example of kind of how our intuitions about high dimensional spaces are completely opposite, well, completely wrong most of the time, and very much opposite of what we would guess from low D space. So just be wary of just any kind of reasoning in those spaces. Just be careful. He's got another actually interesting example of this, and this actually goes back to my point, about the lengths of vectors and things like this. So lengths of vectors in high dimensions. So here we're going to be doing we're going to be looking at Gaussian distributions in high dimensional spaces, and because they're going to be isotropic, so the same in all dimensions, we can just integrate it. We can kind of switch to polar coordinates, and then think about how much probability mass is stored at each radius. So imagine just shells going out to infinity and trying to figure out how much probability is in a given shell. So let me see how much space I have to draw this out. So like it would be, maybe I have some room down here. So it would be like a setting like this, where let's say this would be x1, x2, and you have some kind of Gaussian distribution, and I'm just drawing its contours. And now what we're going to do is we're going to, so this would be R, and now we're going to compute the probability of the probability density along for a given radius. So we know that probability density has to integrate to 1, but the question is how what does it look like? What does the density itself look like? So here we go. So here is what he's going to be talking about. Let me switch back to the laser. So exactly. So we have a Gaussian distribution in high dimensional space. If we transform from Cartesian to polar coordinates, and then integrate out the directional variables. So it says because we are looking with an isotropic distribution, the directions don't really tell us anything. So we can just integrate them out and just look at what the probability density is at a given radius. There's no difference based on direction. So an expression for the density PR as a function of radius r from the origin. So therefore PR delta r is a probability mass inside a thin shell of thickness dr. Okay, and so here is what that looks like. Let me actually get to that. So here's what it looks like for d equals 1. So for d equals 1, that's our normal 1D Gaussian that you're used to. This is a 2-dimensional Gaussian. By the time you get to a 20-dimensional Gaussian, it's starting to shift. You see, it's starting to be kind of quite focused around some value, and it will continue. To kind of shift and get focused more and more as the dimensionality increases. So you start getting this kind of focusing of the probability mass around particular points. So so here we're just talking about that calculation we just did, where we're plotting the fraction of the volume of a sphere lying in the range r is equal to 1 minus epsilon to r is equal to 1 for values dimensionally r. So again, epsilon we want to make, for example, epsilon very small. So let's say for tiny epsilon, like over here, as you would expect, in 1 dimension, the fraction of the volume is very small. But as you can see that as the dimensionality increases, all the way already at dimensionality 20, which is honestly not very big, 80% of the volume is actually contained within that shell, and it just gets worse from there. So that's just going back to that computation we did earlier, showing that even if you pick your epsilon very tiny, like you can imagine, there'll be a curve up here, and very quickly you'll see that as the dimensionality goes up, that almost all the volume will be contained inside there. Okay, so is there anything else? Yeah, so it's just we're talking about, so all this stuff is bundled under the name the curse of dimensionality, and that our intuitions developed in spaces of low dimensionality will that not all intuitions developed in space of low dimensionality will generalize to space of many dimensions. So we already discussed that. Excellent. So now the final question is, well, okay, so if all this stuff is happening, so we said that maybe most real data sets we work with are high dimensional. And high dimensional spaces, like you're going to need lots of data, too much data to actually, for example, do that, that binning procedure we had, and others like it to, let's say, classify data points. The space is so big that you won't have enough data to fill it. How is it possible that we can actually ever do any learning in any of those spaces? And fundamentally, it's because the data usually lives on a kind of a lower dimensional subset. So there's something called the ambient dimension of the data. So that's kind of the dimensionality that it arrives in. So for example, you have 1,000 genes. Okay, so that's a 1,000-dimensional space. But there will be correlation between those genes. So for example, some genes will be coactive or inactive. So that means that those 2 dimensions, let's say there's 2 genes that are like that, are actually 1 dimension. So there will be and so those types of correlations reflect the fact that the data is not uniformly distributed in high dimensions. If it was, we would be hooped. But essentially, the reason why there's anything to study is that the data is not uniformly distributed. It actually has structure, and that structure is low-dimensional structure that allows us to actually learn, have some chance of learning those regularities and then making the predictions we want to make. And then the second point says that the real data will typically exhibit some smoothness properties, so that small changes in the input variables will produce small changes in the target variables, and we can exploit local interpolation-like techniques to make predictions of target for new values of the input variable. So I think what he's trying to say is that, so I guess this is a bit that's a little bit problematic. Successful pattern recognition techniques exploit one or both of these properties. So I believe, so that kind of implies that You either can have the interpolation property, or you can have the lower effective dimension property, or you can have both. But in real life, you're not going to. So if your data is very high, like high dimensional, you're not going to have an interpolation property, just because essentially for the reason that we saw early on, that most new data points will be in entirely new corners of your space. So if your data is uniformly sampled, it won't be the case that if you have uniformly sampled data that's really filling up your space, that a new point you'll be able to interpolate the label of a new point based on the existing data you have, because you just simply will not have enough data. So it's not all possible combinations here will be effective for learning. So you can get away with low dimensionality, and maybe if you don't have interpolation properties, maybe just the sheer low dimensionality of the data and having just enough data will allow you to kind of overcome the fact that your data is very maybe very rough, and so but you just happen to have enough data to kind of fill in the gaps there. Maybe. But so I think the really key aspect is just the low effective dimensionality. So if you have additional interpolation properties, and these are still, whether, for example, in neural networks, whether they can generalize due to interpolation or extrapolation, this is actually a big topic of discussion still, and I'll provide some links in the video description to the current discussion on whether it actually is interpolation. So kind of, having two data points and then classifying a new one, or, based on if by using the fact that it lies within, the span of the existing points to figure out its value. Is that how neural networks are learning? It's still kind of unclear. But it really is important to have this low effective dimensionality in your data somewhere to kind of allow learning to occur. Otherwise, you just won't have enough. You just don't have enough data to do it. And the final bit of the section, he just talks about a couple of points that we touched on. So, he's considering a case where we have some kind of flat objects on a conveyor belt, so planar objects on a conveyor belt, and the goal is to determine their orientation. And so this is actually a very good example of the kind of high ambient dimensionality versus the intrinsic dimensionality. So the data itself in this particular setting will be high dimensional, because the dimensions will correspond to the pixel. So if you have like a modern camera, that'll be million dimensions. So how is it you can actually do this classification? Well, when we're going to assume that objects are identical except for their orientation and location. So essentially, it's because these data, they don't occupy that space of images uniformly. Like, first of all, it's all going to be the same kind of object, so the colors will be the same. The only thing that they will differ along is maybe their locations, so different positions on the conveyor belt, and their rotations. So the set of images will live on a three-dimensional manifold embedded within a high-dimensional space, and that's kind of the key. That's kind of the key observation and the key kind of terminology you will hear all the time. That we have high-dimensional ambient data, but it's embedded on a lower-dimensional space. So, if you want to think maybe more, another example would be kind of, for example, the set of faces. If you look at pictures of faces, well, in the pixel space, that's a high-dimensional space. Millions of pixels again, same as here. But like, not all combinations of pixels are faces, right? So if we just sampled pixels at random, almost none of them are faces. Like, a tiny fraction would be. And that reflects the fact that the manifold of faces is much lower dimensional. And faces, what we would recognize as faces, live in kind of on that low dimensional, possibly very complicated, but low dimensional subset. And he actually does mention, I should have highlighted this. So going back to the example of the objects in the conveyor belt, objects can occur at different positions. Due to the complex relationships between the object position or orientation and the pixel intensity, this manifold will be highly nonlinear. So that means that you're not going to be able to linearly read out to have a kind of a weighted sum of the pixels that will tell you, okay, the object is at this location, this XY location is oriented at 40 degrees. So that's the main difficulty that our visual system, this particular classification problem, has to solve. How you map from the high dimensional pixel space to that low dimensional manifold. and then to extract the variables you're interested in. But the fact that the data lies in a low-dimensional manifold means that you often can do this, and that's kind of how we overcome one of the ways we overcome this curse of dimensionality, by realizing, in some sense, that the data, although it has high ambient dimension, often has lower intrinsic dimension. It actually lives on a low-dimensional manifold, and then we are in a setting where the data sets that we do have might be enough to let us learn interesting things. So that's about it. But the curse of dimensionality, I don't know if it'll come up again later on in the book, but it's a very interesting topic. The reason why our current high-dimensional systems can learn is still being debated. So as I said, I'll provide some links on that. Yeah, and I think for the next session we'll start with 1.5 and decision theory. Thanks.